Hello, everyone. Welcome to the 15th Surface Ventures webinar. So before we go any further, it'd be great to hear from you all and say hello in the chat box. Type where you're joining from. Okay, so while you are all doing that, I'll begin. So my name is Sam McMaster. I'm the events manager here at Surface Ventures, and I'll be your host today. We are a non-for-profit organization, and our mission is to provide world-class surface engineering education for academia and industry. Every month, we will bring you a sector-leading speaker to present the current challenges and future trends in surface engineering. Alongside, we will have surface engineering workshops and live equipment demonstrations. Okay, excellent. Looks like everything's working well. We got even Germany, Sweden, France. Fantastic. Thank you all very much. So today, it will be my great pleasure to introduce Dr. Carl Daube, who will be discussing the tribology of protective coatings in aeronautics. I'll just give some background on Dr. Daube. Carl Daube is an associate professor at the National School of Engineers at Tarbes, where he teaches physics. He has a PhD on the understanding of intrinsic tribological properties of lamellar compounds, and is a permanent researcher of the Laboratoire Genet de Production, specializing in understanding the tribological mechanisms in lamellar compounds, ceramics, metal matrix composites, with the use of Raman spectroscopy, optical profilometry, and tribometry. In terms of agenda, we'll start with the presentation and switch to a few minutes to our partner Brooker, who will be showing some videos today and also releasing some handouts for your information. And we will then come back to the presenter, for your questions. A quick note on questions: you can type these into the chat, and they will be marked for the Q&A session following our partner spot. We will be planning to go for about 60 minutes today. However, this may go over depending on the amount of questions. So apologies if your question does not get answered later, but we must try and keep this event to time. Quick GDPR announcement. As I mentioned, there will be a few brochures and application papers from Brooker. If you download them, someone from Brooker may be in touch later to provide further support. A reminder of our website, Surface Ventures, also. It features videos from our previous talks, information regarding upcoming webinars, and information about the Surface Ventures team. So what I'd like to do now is release a quick poll question to find out a little bit about more about you, our audience. Okay, fantastic. So we've got a good mix there, quite a few undergraduate students, industry professionals, PhD students. Brilliant. So thank you very much, everyone. Right now, I would like to invite Dr. Daube on stage. And
hello, Sam. Thank you.
Thank you. More slides up. There we go.
Well, thank you, Sam, and good morning to all. I would like to thank the Surface Venture team for the opportunity to present our research activities. We work in the field of tribology and more particularly in the framework of non-lubricated friction in dry friction. So this presentation is all about this. So I am a lecturer at the French National Engineering School of Tarbes, located in the southwest of France, near from Toulouse. This engineering school is part of the National Polytechnic Institute of Toulouse and the University of Toulouse. My research colleagues are interested in industrial engineering, process engineering, mechanical engineering, and material engineering. I am conducting work in the latter field of research, more especially in tribology and material characterization. Given our proximity to Toulouse, we focus a lot of our activities on aeronautics and aerospace. Research projects are regularly carried out with the sector of principals and their subcontractors Airbus, Arianespace, CNES, Safran, Liebherr, and JT. So what is tribology? And during this presentation, I will remind you of the definition of tribology, and I will specify the methodological approach that we have chosen at the LGP to conduct our research in this field. I will also present through a case study the problematic posed by wear and an example of characterization, a short example, that can be carried out to understand the mechanisms that takes place in the mechanical system in dynamic contact. With JT, we want to understand how tribological mechanisms operate on coating for aluminum alloy dedicated to aeronautic. And Brucker accompanied us for the realization of tribological tests and the topographic characterization of the surface. The science which studies this problem of friction and wear found its name in the 60s with Professor Peter Just. He defined the science and engineering of interacting surfaces in relative motion by the term of tribology. This neologism is based on the Greek term tribos for friction and logos for study. Although the term tribology is recent, it is a problem that is old as humankind. For example, here, numerous examples can be found in archaeology and show the uninterruptible interest of humanity to decrease the energy dissipated during a mechanical effort. As in this case, a colossal alabaster statue weighing 72 tons that was carried out on the pass of the clay or wood over a distance of 15 kilometers. Here we can see a tribolog. You can see in this reproduction how the ancient engineer involved in the lubrication of this mechanism. In other example prior to this period, tools involving friction for the production of fire was used. In the Middle Ages, solutions were introduced in various fields for the reinforcement and the longevity of structures, for example, with cart wheels. The first tribolog in the 15th century is Leonardo da Vinci, carried out the first experiments on friction. He developed the first tribometer and studied various materials. His work allowed him to propose the two first laws of friction. The first one concerns the proportionality of the forces involved, the applied force and the frictional force. The second one concerns the independence on the phenomena with the considered contact surface. Later, with Hamilton, we rediscover the laws of friction which explain in his memoir for the Royal Academy of Society, the Royal Academy of Science, sorry. Later again, in 1725, in the philosophical transaction of the Royal Society, John Desaguliers discovered the adhesion of solids, and then became, in this study, he interested in the bonding of two spheres of lead strongly pressed against each other. With Charles Coulomb, he studied various metals and woods in dry or lubricated conditions. These experiments take into consideration the contact area, the applied load, the duration of the contact before sliding, and also lubrication. He formulated a relation that takes into account the works of Hamilton and Desaguliers. And later again, we have Irish Hertz, who enriched the static approach of the contacts with the non-conforming contact equation. He made it possible to calculate the apparent contact area between two perfectly elastic solids. It also makes it possible to deduce the maximum and the average pressure in a sphere plane or a cylinder plane contact. In 1950, Baudet and Tabor proposed an approach to contact that has become a classic today. They proposed to explain the friction of two bodies at the level of asperities in the contact interface. This model is broken down into 3 steps. The first steps concern the formation of the contact. There are shocks and interpenetration of the asperities on the real contact area. Plugging then occurs. The normal force contributes to the crushing of the asperities, while the tangential force pushes them away. All this happens under the influence of elastic and plastic deformation. Then the second step is the formation of a junction. The atoms approach each other intimately under the effect of the crushing. There is adhesion and cold microwelding between the asperities, which bring into play the reactivity of the surfaces. The third step is the separation of the contact. The movement can only continue by shearing the junction. Shear then occurs, material is torn away, there is sometimes severe wear, or the interface breaks apart. There is a software. In 1984, Godet proposed the transposition of the model of lubrication to dry contact with the concept of third body. The third body designates a set of intercalary elements bordering the masses in contact, the 2 first bodies. For Godet, 2 body in contact does not exist. The third body can be defined either in the sense of the materials or in the sense of the kinetics. In the sense of the materials, there are interfacial films that mark a zone of compositional discontinuity with characteristic dimensions of the order of 1 to 10 nanometer. For a kinetic point of view, it is a dynamic interface where a velocity discontinuity can be observed. From this point of view, the characteristic dimensions are considered to be between 1 to 10 micrometers. This third body can be artificial, in which case it is a lubricant. It can also be natural and induced by the reactivity of the surfaces or the degradation processes of the surfaces. Godet also brings a powerful conceptual tool, the tribological triplet. This triplet introduces a multi-scale and multi-physical systemic analysis. The triplet is composed of the machine in which the contact occurs, the element in contact, also called the 2 first bodies, and the interfacial element in the third body. The machine or the device is the operating condition. It transmits the loads and the type of stress. The machine plays an important role in the stiffness of the tribo system. The elements in contact, or 2 first bodies, undergo the stress of the device. They react through volume and surface transformation. The 2 first bodies have an influence on the contact geometry and the nature of the material. And the third body is interfacial. They are the interfacial elements. They transmit the load from one solid to the other. They separate the contact element and flows by accommodating most of the velocity difference between the 2 solids. The adhesion and the rheology of the debris flowing the contact are significant. From this systemic view, friction and wear are not intrinsic properties of material, but emergent properties of the tribo system. The example of the VAMAS study illustrates this systemic view. In this study, which involved 31 laboratories from 7 different countries, tribological tests with identical operating conditions were performed. This involved rubbing steel balls against steel planes with the operating conditions noted on the top right of the slides. The results are given very spread information, very spread friction coefficients. And the compilation of these results make appear that there is a huge difference between these laboratories. This dispersion is associated to the fact that there is a lack in the specification of the experimental rig. And this is due to the stiffness of the experiment. This dispersion is due to the stiffness, the difference of stiffness in the experimental rig. To go further, Berthier has described accommodation mechanisms that identify where the energy is dissipated in a tribo system. He lists 5 accommodation seats. The S0 seat is the accommodation of the device. The seat S1 and S2 are the 2 first body. The site 3 is the third body. And he calls also the sites S4 and S5 the surface film. This is the little the film that is appear on the surface of the 2 first bodies. He also called the mechanism of energy dissipation. And with the NAP, he proposed 5 modes of energy dissipation. M0, the elastic deformation, M1, the plastic deformation, M2, the fracture, M3, the shear, and M4, the rolling. In a tribo system, not all these mechanisms appear. You can divide in the following categories the different seats and accommodation energy dissipation. Berthier also proposed to transpose the principle of mass conservation to the tribo system. He called it a tribological circuit. It describes the flow of material from the first body or from the outside, such as a lubricant. We call it QS. He also described the external flow, which is the amount of matter that can return to the contact, and the matter that is definitively lost from the contact. We call this wear. The difference between wear and the source flows of matter permit us to calculate the internal flow or the amount of material associated with the third body. I'm sorry for this equation. This is a minus instead of the plus. So our tribological approach is concerned with tribology. In this science, there is no unifying model and no predictive theory of friction and wear. It's a highly multidisciplinary and multi-scale field that is concerned. And friction and wear are not intrinsic properties, but usage properties of the materials and the tribo system. This phenomena can be discontinuous, transient, or with nonlinear behavior. There is interactive evolution of many parameters, and the contact is many times difficult to directly observe. We have 3 conceptual tools that are currently available to understand this science, this phenomenon. The tribological triplets, the accommodation mechanism, and the tribological circuit. With this tool, we have a multi-scale description of the tribo system. We can identify the local mechanism that allowing the displacement, and we can regroup the different material flows in and out of the contact. Now I will talk about a case study. With the society JET based in Toulouse, we prepare anti-wear coating for application in transport industry and particularly in aeronautics. One of their key products is hard anodic oxidation coating. I will call it OAD. However, this coating uses hexavalent chromium, and Europe recommends abandoning this process through the REACH regulation. JIT has therefore launched the production of the coating that respects the REACH regulation. This is micro-arc oxidation, and I will call it OMA. The micro-arc oxidation permits the formation of semi-crystalline alumina on the surface layer. This alumina layer has two parts, a dense part located directly above the substrate and a brittle part close to the surface. Here is some example of the parts that we can produce. In sometimes this process is used to manufacture vase body or pinion, and parts can be used raw or resurfaced. So what we want is to more understand the behavior of this coating, and now, before the beginning of our study, we have a poor understanding of the behavior of this material. So we launched a project to further our knowledge on this material, and we want to understand the effect of the brittle layer and the performance of the dense layer produced by OMA. We would like also to compare it to OAD coating. So I propose here different parameters in these tables, different mechanical properties of OAD and OMI, like their hardness, and we can see that they are very different from OAD to OMA. Also the coating thickness, and we present also the environmental impact of these two processes. We note that the OAD use hazardous electrolytes, and especially hexavalent chromium, and the OMA is more in line with European regulation. We use for our experiments the Tribolab. This is a tribometer from Bruker. The contact is a ball on plate on a reciprocal translation. The normal load is 25 Newton, frequency 5 Hertz. The stroke distance is 10 millimeter, and we make tests at present tests at 1,200 seconds, but we can make more or less to study the kinetic of wear. We work at 22 degrees of temperature, and the relative humidity can be controlled at 50%. To study the topographic, the surface with and make a topographic analysis, we also use a system from Bruker, which is the Contour X200. And I present here some specification for the measure. Here is some images that we can have from the system after the tribological test. And I present the dimension of the track, and also the representation, the measure on the ball. We see that the length of the surface with a couple of alumina and OAD is very great compared to the other. We will see that this length of 2.12 millimeter is huge compared to the other material. The depth of the track is also important, 209 micrometer. We can measure the net missing volume. It is 2.46 millimeter per millimeter cube. And we see there is a lot of scratch, large displacement of matter. The surface is really damaged and very profound, very deep. On the surface of the ball, there is no loss of matter contrary, there is no damage, no scratch on the surface, and some matter from the plate is stuck on the ball. This is why we have a negative volume during the measure. When we compare this to alumina, a couple of alumina and raw OMA, we see that the length is decreasing. The depth is very low compared to OAD, 30 micrometers, and the net missing volume is 0.5. In this case, I remind you that we have also the brittle part of the coating with the dense part. The friction and the wear is principally due to the production of debris from the brittle part. The surface of the ball is now damaged, and there is debris that spread from the alumina ball in the contact. When we use milled OMA, we use micro balls to resurfacing the coating. We have new lengths and new depths that is approximately the same than with a raw material. The wear track is little less wide, but quite deeper than alumina raw. There is a lot of production of debris also, and we see that we have on the ball damage with scratch, and there is few more debris that are emitted from the alumina ball. Here is the situation in the last case. We resurfacing with we finished the surface on OMA, and the couple alumina OMA give us the smallest and the shallowest wear track of the series. The production of debris on the ball is also low, and the ball is damaged, but we emit less particles. So we can present this and use all this information from the topographic analysis to build tribological circuit like proposed with Berthier. In the first case with OAD, we see that there is a lot of production of debris from the coating and also from the alumina substrate. After that, with the OMA that is raw, we have less production of debris from the coating, but we also have a new flow of matter from the ball. When we have the milled coating, there is not a lot of modification of the production of wear of debris from the ball and from the plane. And with the finished OMA, we have the less production of debris. We reduce the production of debris from the coating, and we also reduce the production of debris from the ball. So we see how we can use the topographic analysis to build a tribological circuit and explain what happened in the contact. We can have also more information from chemical analysis like EDX or ILS, from structural analysis of the phase in contact like with GRX. We can also have more information from mechanical analysis that can improve our description of the tribological circuit and also give information about the accommodation mechanism to explain if there is plastic deformation, fracture, or else. There is also a thermal analysis that can efficiently complete the scenario in terms of energy dissipation. So in conclusion, there is for the moment no laws for wear and friction, and tribological studies required a phenomenologic approach. A systemic approach is effective in solving tribological scenario by using tribological triplets, accommodation mechanisms, and the tribological circuit. We try to understand tribo system in order to move from experience result to control phenomena. So I thank you for your attention, and I'm open to question now.
Thank you very much for that fascinating talk. So for now, we will, yes, if everyone could.
What the role of the brittle layer?
We can do this quick question, and then we'll move on to our videos from Brooker. So sorry, please.
Okay. So Vladimir, the role of the brittle layer. I mean, we have to understand it, and that's what I say when we need to complete this role. The brittle layer is produced when we produce the coating with micro-arc oxidation. We know that the first debris come from the brittle layer, and we suppose that it can participate to the contact. The brittle layer contain again some elements from the electrolytes that we use for the OMR. Now we think that this brittle layer produce abrasive matter, and this abrasive matter participate to the degradation of the first body and the second body, the ball and the plate. So the brittle layer is a huge part of the third body in this case.
Okay, thank you. So we will return to questions momentarily, but for now, I would just like to release a quick poll question from our partner Brooker, and also switch over to our videos, and I'll also be releasing some handouts for that. So for now, if I could ask Dr. Dobe, if you could leave stage, please, while we show the videos. We'll then return for the questions. Thank you.
The R&D guys do R&D, and if it works, I don't see them because it worked, right? But if they're developing something and they start to have some problems, a typical example might be a clutch mechanism. So they basically design these clutch mechanisms, they put them on dynamometers to test them, and if they start to get noise or they don't get the right friction or whatever it is they're after, then they'll bring them to me and they'll say, okay, this one worked, this one didn't, tell me what you can see. So really, it generally starts with a problem. What typically happens, I'll get a phone call. Someone calls me and says, hey, I was referred to you by so-and-so, I've got a problem, right? The problem could be anything, like maybe my brakes are making noise or they're not making noise, okay? So the first question you usually ask is actually what I call the scale of interaction. When you say it's making noise or it's not making noise, do you know where the noise is coming from? Is it indeed the brake pads engaging on the brake, or is something vibrating something else? Because if it's something vibrating something else, it's probably not related to my stuff. It might be a structural problem, right? So we got to deal with what I call the scale of interaction. Once we get it down to that, yeah, this noise is emanating from something like two parts coming together, then it's a question of, well, what's the size of the parts that are coming together? Can I even measure those parts? Or can we cut a piece of the part away? Or if we have to make what we call a replica of the part, where we actually make an impression of the part and measure it. So a brake rotor on a typical car is pretty much the biggest thing I want to deal with. Even truck rotors can, like an F-150 truck rotor, can get pretty big, and it's not that easy to deal with. And so that kind of gives you a feel of the size of the part. But like I say, most of the time the tribology problem you're dealing with is acting over a small size. So once you've narrowed it down to the interacting components, now it's a question of, okay, can I position the parts in such a way that I can measure them, looking for the surface texture differences between them. And for the most part, the instrumentation we have from Bruker can handle pretty much any material. It could be highly reflecting, it could be dull finish. I can measure, black rubber surfaces with a little bit of patience, and you can get a really good measurement of that surface texture. So usually most materials we can measure. The only other thing to watch out for is if the material is composed of any multi-layers of films that are somewhat transparent, then that can cause some trouble. Since we're using an optical instrument, the light kind of goes through those transparent films and cause some problems. So you have to be a little bit aware of that. Other than that, as long as it can fit under a microscope, that's why I usually say to customers, if you can look at it under a microscope, I can probably measure it. And once I can measure it, then it's a question of understanding what the potential mechanism is of failure or problem. If it's a noise issue, if it's a wear issue, if it's a leakage issue, if it's an appearance issue, what is the actual issue? How do they describe it? I have what's called a Bruker NP Flex, which is a 3D optical profiler, which allows measurement of large parts and small parts, both in very smooth situations like a super polished mirror all the way up to a very rough part like maybe a brake rotor or something that's been shot blasted. That's the one instrument I use for surface metrology. And then together with Bruker, we've set up a lab which has a Bruker UMT, which is a universal mechanical tester, which allows the measurement of friction and wear of components by rubbing them together in different configurations, be it a pin on disc, 4-ball test, or whatever kind of configuration you want. So throughout the year, the Bruker people and their experts are here demonstrating the machine and doing projects for people, as well as developing applications for different people in the auto industry.
Tribology is everywhere, all around us. The science of friction, lubrication, and wear provides answers to everyday questions. Which rubber grips the road better? Which coating resists wear better? What material offers the longest life? The lab itself is an experiment in tribology. Before, you needed 7 testers to meet every tribology need. Bruker gives you a complete tribology lab in one universal mechanical tester, configured to run macro, micro, and nanoscale tests, all under real-world conditions. Changing configurations with ease just wasn't possible before UMT. Bruker's UMT makes it quick, easy, and possible. We've combined this with a very large work cell with easy access and great visibility. And all of this helps to keep the focus on the science rather than the tools. We designed UMT for versatility and modified it for excellence in testing material properties, revealing point of failure of coatings by scratch testing, or determining material hardness and modulus through nanoindentation. Bruker UMT delivers versatile tribology and materials testing on a single platform without compromise. Understanding tribology in the lab unlocks real-world product functionality. Tribology is all around you, and Bruker is here to help you with locations around the world.
Okay. Hope you all enjoyed those videos, and I would like to return to Bilbe for the remainder of the questions. If you have any more, please go ahead and type them in. So you have the question of how is the height loss of the ball measured?
So the height loss is measured with the profilometer, with the contour X. So we use the ball on the profilometer, and we make a record of the surface, and after that we treat the image to measure the distance of the part that is lost from the ball, and we also treat the image to put it flat. In this way, we see appear a hole in the ball, and then we can measure at different points the height that is loose in the ball. We can try also to see if it is a geometry that is conform with the sphere. Sometimes yes, sometimes no, and we can use also analytical equation to measure it also.
Mm-hmm. Excellent. So another question: what are the practical applications for this research?
Okay, one of the huge application is for the aeronautic. We prepare some parts for a system for evacuation of gas, or also this is what I showed before. I don't remind me the name in French. In English, sorry.
Okay. Would you like me to bring the slides back up? Would that help?
Yeah, exactly. This is for the protection of this part that are in friction.
Please.
And they use, sometimes they use the coating raw, and sometimes they use it resurfacing. And we try to understand if it is necessary to make another operation of the surface, or if we can do one is less expensive, you see.
Okay. Thank you. And another question here: any specific reason of wear of the balls despite having good surface finish on the counter surface?
Any specific reason of wear of ball despite having a good surface finish? Despite having good surface finish. The wear of the ball is something that we don't really control, because the surface the brittle part emits a lot of debris, and these debris are very hard, and the ball is then involved in the production of debris. We don't really control that. With the OLD, with the first coating, the surface is smoother, and then the ball don't produce wear, but the surface is really damaged in a severe manner. In another way, we need to find a balance between the loss of matter with the ball and the loss of matter with the plan. We don't in the real situation, in the situation that I show, we work with alumina ball because we need to really impact the surface to see the wear of the alumina on the surface, not of the ball but the coating. In some other application, in real application, we put in front of the coating metal parts, metal parts, and in this way it is smoother, and there is less wear from the coating and more wear from the ball also. And the third body is also very different. So in this study, we really want to see how the coating can be affected by a very strong ball. And we would like to see if the way we change the surface by milling or by finish it can affect the condition. We thought at the first time that the production of debris can protect the surface by transmitting transmitting the speed and transmitting well by giving a good accommodation. But we see that by finishing the surface, we produce less wear, we produce a few debris for the third body, and it's more efficient, it's more effective.
Okay. Another question here from...
Hello, Bordeaux.
This is greetings from Bordeaux. In my company, we've had some contacts with customers who wanted to test different types of coatings on the sample and the ball. We mostly use ceramic, steel, or stainless steel balls. Our choices are limited. Do you know some suppliers who can prepare balls on demand? Does Brooker do that?
From myself, I have some suppliers, Aurélien, and if you want, I can give you my contacts. We have in France two societies. There is a CIMAP and also another one. But there is also from Bruker we have metal balls. I don't know if Daniel is there. He can give you more information. I can give you my contact if you want. No problem.
Here's Daniel now.
Hi everyone, can you hear me?
Yes,
Yeah.
we can hear you.
Yeah, very good question. And no, we don't. So we have standardized, but just yesterday someone asked me if I can get a silver coated ball for a test on an electronic conduction line. So this is not so easy. With the help of Dr. Delbé and others, we set up we have some suppliers around Europe that can help us, but no, we don't supply specific coated balls. This is the official, but you can reach out to me and or Carl, and we may give you some names of suppliers where you can knock on the door and ask if they're going to do this for you. Thank you.
There we go. So that was so we just wait a minute or two to see if we have any further questions from any of the audience. That's all right. I'd just like to remind everyone that the handouts from Bruker are available for download on the handouts tab if you'd like to find out any more about the Tribolab systems and a little bit about thin film and coating testing. Just give people another minute or two to check that they're not finishing typing long questions.
And Sam,
Okay.
what about you?
Doesn't
You
look-
were interested in coaching also, I think.
Yes, very much so. My sort of focus has been in coatings, nanomechanics, and how that can help explain the tribological properties of coatings and sort of various different types of characterization of them, threatening wear, impact and erosion, quite a few different things. But yeah, but yes, very. But yes, with that, I think we'll. Looks like we don't have any further questions, so I would like to say thank you very much for your fascinating talk. Let me just move on to our final slide. Excuse me a moment. There we go. So yes, thank you very much for your brilliant talk today and for answering those questions. I hope everyone was. Oh, we got one final. Okay, sorry, we do have one final question there, and since we are running ahead on time, I will answer that, and then no further questions after that. So that is, what different types of coatings for aerospace applications?
Oh wow, it's a huge question.
Good question to finish on. Good question to finish on.
Yeah, it's a good question and a huge one because from myself, I don't know all of them. There is a very interesting study from Holmberg that give a lot of make a very beautiful review on the applications and the coatings for different industries, and it also show different way that coatings are the degradation appear with wear from different coatings. I really advise you to see this publication. Maybe Dr. Baratish, if you want, I can try to send you this reference for this review.
So long as Dr. Baratish is happy with that. There we go. I can pass on that email address, and also I will also pass on the email address of previous question we had about different suppliers. So we'll do that after this webinar. So sorry, with that, thank you for that final question. Thank you for answering that final question. And yes, thank you very much for the fantastic talk. So as we draw to a close now, I would just like to say thank you very much to our partner today, Bruker. We would not be able to run our sessions like this without our partners. If you're interested in further content from Surface Ventures, please visit our website. The link is on screen at the moment. We will be looking to organize our next webinar on the 25th of November. But please check on our website, on our mailing list if you would like to join that, available on the website, and our LinkedIn for further updates on this event. We also have our fortnightly newsletter, Modern Surface. By signing up to our mailing list, you'll be able to receive that. It's written by myself, so if you would like some of the latest and greatest from surface engineering, please sign up to that newsletter. And I would also like to ask, thank you all to the audience for attending and for your support. And please, for future events, please do take the time to advertise these to your contacts, to your colleagues. We would greatly appreciate it to help sort of spread this to more people. So with that, I would say thank you all very much, and thanks for joining today, and have a great rest of your day, everyone. Thank you once again.
Thank you. Bye-bye.
Thank you all. Goodbye.